Hello friends, welcome to Truth of Physics. Today I will discuss on the concept of mean free path, and also in this video I will derive the expression for mean free path. This is the topic from kinetic theory of gas. So we all know that from the assumptions of kinetic theory of gas that there is a random collision between the gas molecules, right, in a gas, and the motion of gas molecules is completely random. Now what is our mean free path, and why we have the requirement of mean free path? Now what is free path? Free path of a molecule, gas molecule, is the trajectory of that gas molecule in a gas. Okay, this is called the free path. And what is mean free path? Mean free path is the average of the free paths. This is suppose here is a molecule, gas molecule, and after some time this is colliding with another gas molecule here. Okay, so here is a collision, and after that collision this molecule will go in this direction and our previous molecule will go in this direction, suppose. So here is our previous molecule, and now here will suppose here one more collision is occurring. So after some successive collisions this will look like this. So the trajectory of our molecule, of our test gas molecule, is like this. This is completely random and zigzag. Okay, now how we can find the path, the free path? Okay, because all the distances, all the lengths of the free paths between the collisions, that is first collision, the length of the first collision, the traveling distance between the first collision, the distance between the second collision, the distance between the third collisions is completely different, and we do not know the relation between these distances. Okay, so that's why we have to calculate the mean or the average free path. Now what is mean free path? We are denoting the length of the mean free path with lambda. So our mean free path lambda is equal to lambda 1 plus lambda 2 plus dot lambda n, suppose, divided by n, where n is what? N is the number of collisions executed by one gas molecule. Suppose this is our gas molecule. So this molecule will execute n number of collisions. Okay, and what are these lengths? These lengths are simply this is lambda 1, suppose, this is our lambda 2, the consecutive path difference or consecutive distance between the collisions. Okay, this is lambda 2, this is lambda 3, and in this way there are n number of collisions and there are n number of free paths. Okay, now this is the mean free path. This is our mean free path. Now we can write this with another form. What is this? We can write this like this: V average into T. Suppose the n number of collisions is occurring in the interval T, in the time interval T. That is, after time T, the gas molecule is executing n number of collisions with another gas molecules in that gas. So, and V average, this is V average. Okay, the average velocity or average speed of the gas molecules. So this is the distance after time T, that is, this is the distance after n number of collisions. Okay, distance traveled by that gas molecule after n number of collisions. So we can write also this is the length, this is the length, total length after n number of collisions, and this is also the length, because we know that S equals to Vt, right? So simply this is the length Vt and divided by n. Now one or more another thing, that is T by n. What is this? Suppose there are n number of collisions and this collisions is occurring, n number of collisions is occurring in the time interval T, right? So we can say that the time interval between two successive collisions, that is the time interval between this. So this is what? This is t by n, and we are denoting this with tau. Okay, what is this? This is the mean time between two successive collisions. Okay, this is the mean time between two successive collisions. Now we all know that what if this is the mean time between two successive collisions, then what will be 1 by tau? This will be nothing but the frequency, and in this case we will name this collision frequency, or simply P, capital P. Okay, so this is our collision frequency. So in terms of collision frequency, we can write the mean free path like this: lambda is equals to V average divided by P, that is the collision frequency, PC. Okay, PC, collision frequency, P suffix C. So this is the definition of mean free path. Now we will derive the expression for mean free path. So I am cleaning this. Now our motive is to find the value of PC, and then we can derive the expression of lambda. Okay, now how can we find PC, that is the number of collisions per unit time? How can we find this? So for this we have to assume one thing, that is called the zeroth order of assumption, or zeroth order approximation. So what is this? As the motion of the gas molecules is completely random, right? The motion of gas molecules are completely random. So at an instant of time, or at a interval of time, small interval of time, there are random collisions and random motion of gas molecules. Okay, now to find the lambda and to find the collisions, we have to make a assumption, that is all the molecules are freezed with time. We are considering this for a small time, very small time. All the molecules are freezed, or all the molecules are stationary, and there is only one molecule present which is moving freely, and this is what? This is called the test molecule, test gas molecule. So we are assuming this, and all the molecules surrounding this are fixed. This is called the zeroth order approximation, and in this video I will derive all the things on the basis of the zeroth order approximation. Now all the gas molecules are, the shape of all the gas molecules are rigid spheres, right? We all know this concept from the basics of, or from the assumptions of the kinetic theory of gases. Now suppose the radius of our gas molecule is r, okay, and the diameter is d. So d is what? D is 2r. Okay, remind this, d is 2r. Now we have a test molecule, right, which is moving in a straightward direction. Suppose this is moving freely in a straightward direction. So after a time interval t, this will move, or this will travel a distance v bar t, that is the average velocity into time, this distance. Okay, so this molecule is traveling this distance after a in a certain interval of time t. Now all the stationary molecules are available in surrounding this molecule, right? All the stationary molecules, or all the freezed molecules of the gases, and this is only moving. So this is tracing a area, right? Now you have to think it carefully, that a gas molecule which is basically a rigid sphere. Okay, imagine that I have a rigid sphere, and this is moving in straightward direction. So just imagine that this is sweeping out while this is moving in straightward direction, this is sweeping out a area or a volume. This is sweeping out a volume, and that volume is what? The volume of a cylinder. That is, when the sphere is moving along a straight line, this is sweeping out a cylinder, imaginary cylinder, and what is the area of the base of the cylinder or the radius of the cylinder? The radius of the cylinder is r. Okay, now for collision for occurring a collision, what are the necessary conditions? We will understand this now. For occurring collisions, the all the other molecules which are present across this molecule, okay, all these molecules must have to at least touch this line, right? That is, the molecule, assume that all the gas molecules are of same shape, okay, the same radius, okay, the same volume. So this is our gas molecule, okay. So to occur a collision, the another molecules which are freezed must be in this region, or must be at least touch or at least cross this limit, this dashed line, right? This molecule must have cross or just touch this line, so that the collision with this test molecule will occur with this stationary molecule. So we can say that the center of that molecule, the freezed molecule, is here, right? So the center of the freezed molecule is here, and our test, this is our test molecule, okay. And here in the both sides, that is in this side and in this side, will be the same case. So we can say that the surface of the another gas molecule must touch these dashed lines. The surface, this is the surface, this is the surface, this is the surface of the another gas molecules, and this must touch this dashed line to occur a collision with the test molecule. We can also explain this with one another aspect. What is this? If we draw this dotted line or this dashed line, then what happens? Then we can say that this is the center of that molecule, the freezed molecule or the stationary molecule, right? So we can say that the center of the another gas molecules must be at least on or into this dashed line. The center of another gas molecule must be into this dashed line, that is like this, or must be at least touch this dashed line, the center, okay. For what? For occurring collision with this molecule, okay. So we can say that this is what? This is a imaginary cylinder which I have previously discussed. This is the imaginary cylinder, and the radius of the base of that cylinder is what? This is the radius, and this is what? This is this length, and this is this length, and this is what? This is r plus r, that is 2r equals to d. From here we can write that this is d. So what is this cylinder? This is the cylinder, this is that cylinder in which the center of the gas molecules will cross. If the center of the gas molecule will cross the boundary of this cylinder, then collision will occur with the test molecule, right? So we can say that the number of molecules, suppose the number of molecules present in this imaginary cylinder is n. Suppose this is denoting, I am denoting it with n, number of molecules present, number of stationary molecules present in this imaginary cylinder which is sweeping out by the gas molecule, or by our test molecule at the time interval t, okay. Now this is what? This number will be what? The number of gas molecules present in this region will be what? will be equal to the number of collisions, right? The number of collisions. So why I am writing this? Because suppose there are 3 molecules present. So if there are 3 molecules, then there will also be 3 collisions. There will also be possibility of 3 collisions with these 3 molecules. That is, so I am writing this, that if there is n number of molecules, then there will be n number of collisions. So we can find the number of collisions, right? Now we have to find this number n. That is how many molecules are present or can be present in this region or in this in the volume of this imaginary cylinder. Now if there are n, small n, if there are n number of molecules per unit volume in the gas, there are n number of molecules per unit volume in that gas, then we can say that in this volume there will be a number, the number of molecules present in this volume will be what? Will be this density. This is number density, basically the number density n into the volume of this imaginary cylinder. And what is this? The volume is what? Pi r square into h, and here h is this, and pi r square is what? Pi into d square, right? This is the radius of that imaginary, this is the radius of that imaginary cylinder, and this is our h. So this will be pi d square into v bar t. Okay. Now this term pi d square, right? This term pi d square, this is the number of collisions. Number of collision. In number of collision in the time interval t, in time t, right? This is this. So this, and this term pi d square, this is denoted as sigma. Okay, you have to remember also that sigma is what? Sigma is equals to pi into d square, where d is what? D is 2r, 2 into the radius of a gas molecule. Sigma into v bar t, sigma v bar t into n, n sigma v bar t, and this is this. So the number of collision per unit time will be what? We have to divide this with t. That is, that will be and the number of collisions per unit time is what? The collision frequency, and we are denoting it with Pc. Okay, so the Pc will be what? Simply this divided by t, that is n sigma v bar, right? So we have at last we have found the expression of Pc, that is collision frequency. And remember that what was our lambda or mean free path? Lambda was equals to v bar by Pc. So v bar divided Pc, that is n sigma into v bar. So this will be equal to 1 by n into sigma. So this is our lambda, or this is the mean free path. This is the expression, standard expression for the mean free path of gas molecules. So where sigma is what? Sigma is our microscopic collision cross section. Okay, microscopic collision cross section. It is sigma. And what is n? N is the number density or number of gas molecules per unit volume. Now this expression can also be transformed in another equation using the Clapeyron's equation. So what is Clapeyron's equation? I am assuming that you all know that Clapeyron's equation is what? P, that is pressure, P is equals to N kBT. K is what? The Boltzmann constant. K into T. K is what? The Boltzmann constant. So this is our Clapeyron's equation. So from here we can write that N is equals to what? N is P divided by KT. So if we put this here, so lambda will be what? Lambda will be lambda is equals to KT divided by P into sigma. KT divided by P into sigma, where T is what? T is the temperature, K is the Boltzmann constant, N is N. I have discussed what is N, and P is the pressure. I think that you have understood all the concepts that I have discussed in this video. If you have any doubt, then you can also comment below in this video, and I will also discuss that or also explain that. So take care of yourself. Thank you for watching.